Hi again. In this video I will be solving two examples. You can tell almost the same example, but the idea is to show you it's not how much information given by the question, it's about how you can use the formulas and how you can connect the concepts between the potential difference and the work and the potential energy and all these forms, how they can be related and connect to each other to help you get the answer. For the first one, an electron is placed in an electric field with a magnitude of 5000 volt per meter, right? Directed to the left. So I know where is the direction of my electric field now. Caused by two charged plates 1 meter apart. Starting at the left plate, the electron zips across to the other plate and emerges through a hole. How fast is the electron moving? All right, let's first, as usual, let's sketch something. I have my first plate as my second plate, and it says the electric field is going to the left. That's my electric field. I will say E. So as we know, that will be the positive plate, that will be the negative plate. Now I know that the electric field equal 5000 volt per meter. The distance between the two plates is 1 meter. But this time it's not asking about the potential difference between the two plates or how much is work required to move this electron between the two plates. It's asking about how fast this electron is moving. Now let's draw this electron. That's the electron, okay, and it is E. It's going from starting at the left plate. All right, so it's starting from speed 0 from rest and will zip through this little, let's make a small hole. That's where the electron will be going through. It's just gonna be zips through this little hole. He's asking me to find how fast will be that electron when it's crossed that hole. Okay, now if you think about the energy conservation rules and the way we learned it before in the mechanics, you should remember that work equal change in kinetic energy. So in our previous examples or videos, we discussed that the work equal the negative change in the potential energy. But also you need to keep in mind that the work equal the change in the kinetic energy, which means, all right, that it is the kinetic energy final minus the kinetic energy initial. Now, what about the work? Well, I know that the work equal Q E times the distance between the two plates. Because I know how much is the charge of the electron, I know how much is the electric field between the two plates, and also I know the distance between the two plates. Now, initially, there was no kinetic energy. So starting from rest. So that part is gone. Now, we know that the kinetic energy, it's a half mv squared, and we can call it V final. Here it is Q E distance. So if I want to rearrange my formula, it will be the final speed equal to Q E times the distance over the mass, okay? And from there I can take the square root, and that will be 2Q E times distance between the two plates over the mass of the electron. We can write ME here just to make it more clear, and from here 2 times 1.6 10 to the power minus 19. The electric field is 5,000. The distance 1. And the electron mass is 9.1, 10 to the power minus 31. All this will be under square root. And the answer will be 40, almost 42, 10 to the power, positive 6 meter per second. And that's really speedy. It's almost like about probably 10 times the speed of light, almost. Anyway, so that's the speed of our electron when it zips through that little hole on the positive plate. So the main idea of this example is to remember that there is a relationship between the work and the change in the kinetic energy. If you go back to the previous videos where I was explaining the relationship between the work and the potential energy, I said in both cases where the object was falling or the charge going from the high potential difference from high voltage to the lower voltage, in both cases the two objects, or the charge as well, the charge and the object, they were accelerating, or they were getting a kinetic energy. So the loss in the potential energy is practically gaining a kinetic energy. I hope these things make sense to you. So let's try to solve the same example, almost the same example, not necessarily the same numbers, but the same meaning or the same idea. Okay? See, here's the example. It says calculate the final speed of a free electron accelerated from rest through a potential difference equal of 100 volt. All right. So once again, well, we know that again the work equal the change in kinetic energy, and it is half mv final square minus half mv initial square, and that will be 0 because it's starting from rest for the work. Now in our previous example we used the formula, the Q times the electric field times the distance. In this example, that will change the color. I'm not gonna use this formula because I don't have an electric field. All right, I only have an electron and a voltage difference between the two plates. So I have to use Q times delta V in this case. So I will end with that Q, the change in potential difference, please don't mix that with the velocity, equal half mv final square. So the v final square will be 2 times q, change potential difference over the electron mass, and from here I can say the v final equal 2q, change in potential difference over electron mass under square root. You just need to put the numbers. It's 100, yeah, divided on a 9.1, 10 to the power minus 31, and all under square root. And this should give you, let's try it quickly. It's 2 times. That, all right, this will give us about a 1 value of, yep, sorry, pen. It's about 6 10 to the power 6 meter per second as the speed of, or the velocity of this electron based on this condition. So this example, it's as a start is the work and the change of the kinetic energy as the one before, but I show you that how I can switch or connect the work with the potential difference in this case, and in the previous one where I connect the work with the electric field to get what I want from the question. All right, I hope you find this video useful, and hopefully I see you in other videos later on. Thank you.